Hello everybody, let's begin chapter 5. So what I'd like you to do is first take a second and copy these notes down for the beginning of chapter 5. Here we're going to talk about discrete probability distributions and what those mean. It'll take a day or two to actually get through it. So here for a random variable, it is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. So this is some blah 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 blah. And let's look at this other blah blah. This is a probability distribution. It's a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. So let's go through an example to try and make some sense of what these definitions mean. So within the email or within the notes, we should have this. My printer was really bad, so it cut off the cube and some of the font is a little faded, but I think we'll be able to survive. So from your first page, I basically just typed out these notes for you, and let's look at the first part over here. Let me zoom in. Okie dokie. There's a glare, and I think that's good. Okay. Let me fix this, that. Okay, so here, the first part it's saying, construct a probability distribution for rolling a single die. So let's just go back to the definition of probability distribution. It's saying that we need to give a description that gives the probability for each value of the random variable. So what are we talking about here? It's saying, let's say we have a die. So let me actually get a die, right? Okay, so I have a die. Now it's saying, what is the sample space for rolling a die? You could roll a 1, you could roll a 2, a 3, a 4, a 5, or a 6. And it's saying, what is the probability distribution? So simply, it's just, what's the probability of getting a 1? It's 1 out of 6. What's the probability of getting a 2? It's 1 out of 6. And we just have 1 out of 6 for all of them. And that's the idea of a probability distribution. What you're saying is, you're just writing all the outcomes, all the possible outcomes, given some sort of situation that's occurring. Okay? We'll go through another example to make a better feel for this. So, yeah, let's take a look at my notes. Let's see, this page over here, what did I write? So yeah, we just did this, so we construct a probability distribution, okay? Let's look at the next page over here. What is going on over here? Okie dokie. Yeah, this one. Okay, so here, let's take a look at this scenario here. It's saying, represent graphically the probability distribution for the sample space of tossing 3 coins. Okay, so let's imagine we have 3 coins, right? I have 2. Imagine there are 2 more, right? So what is the probability that if you toss 3 coins, you'll get 0 heads, 1 head, 2 heads, or 3 heads? Okay. We have to go through these possibilities. So let's imagine if you toss a coin, right? The first coin you toss, you're either going to get a heads or a tails, okay? And now this is for the first coin. So this is coin number 1. Okay, what about coin number 2? All right, what could happen if you have a second coin? What can you get? Well, let's say the first flip is a heads. After the heads, you could get a heads or a tails. And what if you actually got the tails in the beginning? You could still get a heads or a tails for the second toss. And let's say if you have this third toss over here from the heads, you could get another heads or a tails. Here you could get a heads or a tails. Here you could get a heads or a tails. And from this tails, you could get a heads or a tails. So what's the idea behind this? So let's see, outcomes. Notice that if you have 3 coins, you could get the first flip could be a heads, then a heads, and then a heads. Okay? What about another possibility? You could get heads, heads, tails. You could get heads, tails, heads. You could get heads, tails, tails, and then what else could happen? You can get tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay. So these are all the possibilities. Notice that how many possible outcomes could occur from flipping 3 coins. There are 8. There are 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So notice, let's go back to this question over here. What's the probability? Now notice these are all the outcomes. What's the probability that you get no heads? Notice which one of these satisfies no heads at all. It would be this one over here. And notice that how many are there? There's 1 out of 8. Let's try and go through the next question and try it by yourself. Here, how many possible outcomes are there where you only get 1 heads? Notice here, there are 3 heads, so no. 2 heads, 2 heads. This has 1 heads over here, and this one as well. Okay, so notice that here, we have, is there another one? Am I missing it? Ah, yeah, this one too. My bad. This one only has, you see, notice how these 3 only have 1 heads. So how many are there? There are 3 out of 8. Okay. What about for the next one? How many situations are there where you have two heads? So here it would be this one, and this one. So notice that this is 3 out of 8. And what's the how many ways? What's the probability where you get all 3 heads? This will be just 1 out of 8, which would be this one here, which is 1 out of 8. Okay, and that's the idea of a probability distribution. It's just stating that what's the probability of getting, out of 3 tosses, of getting 0 heads? It's 1 out of 8. 1 head, 3 out of 8, and so on. Okay, and what we could do is, this part it's saying you could show a graph. So what's the idea of showing this as a graph? Here, basically, oh, this is very faded, I'm sorry. But the idea is if this is 0, 1, 2, 3, and if this is 1 out of 8, 3 out of 8, I'm sorry, 1 out of 8, 2 out of 8, 3 out of 8, well then what's the probability of getting 0 heads? It'll just be 1 out of 8. 1 head is 3 out of 8, something like this, right? And this is, 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. Okay? Alright, that was just the little warm-up of getting a probability distribution. Alright? Let's go through the next example. Well, actually, here, I remember I wrote this in my notes a while back. Maybe it'll help. Let me zoom out. So here, this represents graphically the probability distribution for the sample space for tossing 3 coins. So here, we already talked about this. What is the probability after 3 flips that we receive 0 heads? It's 1 out of 8. What is the probability after 3 flips that we receive at least 1 head? This is 3 out of 8, and so on. Okay, so I thought maybe this little dialogue would help you out. Okay, let's look at the next and final scenario or the final example over here. Let's take a look at this. Let me zoom in. What I'd like you to do is take a second and read this by yourself. But here we could read it together if you want. It's saying the Baseball World Series is played by the winner of the National League and the American League. So we're going to talk about baseball. I don't know who's a fan of baseball. I never played baseball growing up. I played basketball. But what's happening here is for the World Series or the championship game, it's a best of 7. Okay, so the first team to win 4 games wins the series. Okay, so the series will consist of 4 to 7 games depending on the individual victories. The data show consists of the number of games played in the World Series from 1965 to 2005. There was no World Series in 1994. The number of games played is represented by the variable x, and it says find the probability of p of x for each, construct a probability distribution, and draw a graph. So notice here that if we were to draw this out, so here, what's the setup? Here, if we had a number of games, and we're going to represent this as X. Notice how many games you could have either played 4, 5, 6, or 7 games. Okay, and if we had the probability of P of X, notice how many games were there where there were only 4 games played. There were 8 out of let's see, this is what, 40, right? Yeah, 40 games. Okay, because if you count 8 plus 15, 24, 40. Yeah. Okay, so then what about here? This is 7 out of 45. I'm sorry, 7 out of 40. For 6 games played, it's 9 out of 40. And here we have 16 out of 40. Okay, and you could have actually showed this instead of fractions. We could have showed it as decimal. So instead of 8 out of 40, we could have said, you know, 0.200, 0.175, 0.225, and 0.400. This could have also worked. But what's the idea behind this? Like, why is this? Sorry. This is what I wanted to get for you. Here, what can you infer from this data? Right? So imagine, let's go back to the scenario. Here we're talking about the World Series, right? And imagine if you're the 2 best teams, right? This is team number 1 and this is team number 2. And notice that throughout the 40 or so years, out of every World Series, only 8 games went to 4 games, where the team, this is basically a sweep, right? 7 of the games went to game 5, 9 of the games went to game 6, and 16 of the games went to game 7. What can you infer from this data? Okay, so if you pause the video and you wanted to write down or think about it, most of the teams were even, because if you go to of the majority of the games went to game 7, it's saying that the 2 best teams were very, very close to each other. Let's say if it was the other way around, where it was 16 over here and this was 8, then this data is stating that one team was more dominant each of the years than the other team. Okay, I think that'd be pretty interesting with something like basketball or other sports. Like in basketball games from like 1965 to 2005, were more of the games sweeps or were more of the games very close? You know, it might be different in like basketball and baseball, but something for you to think about. Okay, this will just be a short video. And oh, actually, I'm sorry, one more part. This part over here, and then we're done. So let's take a look over here. Oh, this is very faded, my bad. It'll probably be much better when you print it. But yeah, this was what we just talked about here, and here's a little graph you could copy if you want. Okay, 2 requirements for a probability distribution. So basically what this is stating over here, I just wrote it down over here for you to copy. Here it's saying 2 requirements for a probability distribution. So what are the probability distributions that we've been talking about? It's these scenarios over here. All right, so what are the 2 requirements? Here, number 1, the sum of all probabilities of all events in the sample space must equal 1. That is, sigma, or the summation of all the probabilities, must equal 1. What does that mean? If we go back to the first example, what was the first example? Over here, let's just go back very quickly. Here, notice that what happened when you added up all these probabilities? What is 1 over 6 plus 1 over 6 plus 1 over 6? When you added all these probabilities, notice that you have to get 1. What was the next situation we had? I think it was flipping the coin, right? Where was it? Yeah, over here. Notice that for flipping the coin, in this scenario, what is 1 over 8 plus 3 over 8 plus 3 over 8? This is equal to 8 over 8, which is equal to 1. All right. And what was the last situation that we had over here? With these probabilities that we had, what was this? 8 over 40, 7 over 40, 9 over 40, and 16 over 40. Notice you get 40 over 40, which equals 1. And that's what that's what it's stating over here. It's just saying that the sum of the probabilities must equal 1. Okay? And let's look at the next scenario. The probability of each event in the sample space. So it's saying that these fractions over here, you see like 8 over 40, 7 over 40, 9 over 4. Oh, that's completely wrong. Sorry, that should be 9 over 40. Notice that these fractions over here within the probabilities, they must be between 0 and 1. You can't have a probability of something being a negative value, like negative 0.25, or saying that the probability of something happening is 1.73. Your probabilities must be between 0 and 1. Okay? So looking at this scenario over here, let's take a look, and we're almost done. It's saying determine whether each distribution is a probability distribution. So looking at example A, does example A satisfy condition 1 and 2? Okay, and hopefully you copied condition 1 and 2 down. Let's see, condition 1, and I'll just write it here. So condition 1, that P of X must, the summation of P of X must equal 1. And condition 2, it's that each probability must be between 0 and 1. Okay, and let me fix this blur. My bad. Okay, so let's take a look at letter A. Does letter A satisfy the two conditions? Well, if you add up the probabilities, do you get the summation P of X is equal to 1 over here? Yes, because what is 1 over 5 plus 1 over 5 plus 1 over 5 plus 1 over 5? It's equal to 5 over 5, which is equal to 1. So the first condition is okay. Now let's look at the second condition. Is each one of these probabilities between 0 and 1? Yes, because what's 1 over 5? 1 over 5 is 0.20. And notice that 0.20, or 0.2, is between 0 and 1. So both these conditions are satisfied for the probability distribution of A. What I'd like you to do is try and go through B, C, and D and just ask yourself, does it satisfy both conditions? And what I'd like you to do is pause the video and try and go through it. Okay, so for letter A, it was yes. What about letter B? Does letter B satisfy the condition? No, for two reasons. Notice that P of X, if you added all of this up, you got P of X equals, what does it equal? Negative 1, 1.5. This is, I'm sorry, here, I just spaced out for a second. Notice that one of the probabilities is negative. So already it fails the second one, okay? And yeah, so that for letter B, it failed the second condition. What about letter C? This was a yes, because what is 1 over 4 plus 1 over 8 plus 1 over 16 plus 9 over 16? Notice that how do you add these fractions up? You can convert this to 4 over 16 plus 2 over 16 plus 1 over 16 plus 9 over 16. And then this becomes 6, 7, this becomes 16 over 16. So it does equal 1. So for this part, it's okay. And for the second part, it's also okay because each one of these probabilities is between 0 and 1. Okay? And what about for letter D? This was a no because sigma P of X, what happens when you actually add the probabilities? What is 0.5 plus 0.3 plus 0.4? This is 1.2. And notice that it's not possible for the probabilities to be all the probabilities when you combine them together to be 1.2, it has to be a 1. Okay? Whew. All right, everybody. Happy face. So this was just kind of a little lecture. So we did chapter 5.1 and 5.2. So the real beauty of this section is 5.3. Okay? So we're not going to there's no homework for this section. And 5.3, I'll have a little assignment for you guys. And I'm going to have this video right away. So I'm going to work on it as fast as I can. But what I'd like you to do is just for what we did today, just take it in, have the notes, and 5.3 will be the actual lesson where we'll actually learn a lot of cool stuff in 5.3. Okay? I hope you enjoyed this video. I hope you're all safe. I'll talk to you soon.